Hello, and welcome to a place of gentle wonder. I'm truly grateful you found your way here tonight. Perhaps the day has been long, filled with noise and motion. Or perhaps you simply find comfort in letting your mind wander among the mysteries of existence rather than counting imaginary sheep. Whatever brought you here, this moment is yours. There's nothing you need to do, nowhere you need to be. Just let your shoulders drop, your breath deepen, and your thoughts begin to soften like morning mist dissolving into air. Tonight, we're going to drift back through time itself, back to something so profound that it sits at the very threshold of what we can know, the origin of everything, or at least the earliest whisper of beginning that science can reach toward. This is a story not just of light and matter and the fabric of space, but of boundaries, of what it means to truly understand something, of what it means for a moment to even be real. But don't worry, we won't rush. We'll move gently, thoughtfully, like water flowing through a quiet stream. And before we begin our journey, if these peaceful explorations through time and cosmos bring you comfort, if they help your mind settle after the day's demands, consider offering a soft tap to the like button. It helps these whispers reach other wandering souls who need them, one peaceful heart at a time. Now, let us begin, not with thunder or flame, but with something quieter, a question that rests beneath nearly everything else we might ask, a question so large it seems to shimmer at the edges of thought itself. Where did everything come from? It's the kind of question that feels impossible to hold in your mind all at once. Larger than mountain ranges, deeper than oceans, vaster than the space between stars. And for a very long time, science didn't attempt an answer. After all, how can you measure the birth of time when time itself is what's being born? How can you describe the beginning of space when every tool you have for describing things requires space to already exist? But that silence, that mystery, didn't last forever. Early in the last century, something began to shift. Not because someone discovered the answer lying in wait, but because subtle clues started appearing. Observations made through telescopes, patterns emerging in data, faint fingerprints scattered across the night sky like traces of something ancient. And gradually, piece by piece, a picture began to form. A quiet but undeniable suggestion that the universe itself is not frozen in place. It's growing. The distances between galaxies are increasing, not because they're racing away from each other like scattered leaves, but because the very fabric of space is stretching everywhere, all at once, like a canvas being gently pulled at its edges. The notion of a changing cosmos felt uncomfortable at first. For centuries, humanity had imagined the heavens as eternal and unchanging, a great clock ticking forever in the same rhythm. Even Einstein, when he first glimpsed the implications hidden within his own mathematics, introduced an adjustment to keep the universe static, not because the equations demanded it, but because a universe that moved and changed felt too uncertain, too unsettling. He would later reflect on that choice with regret, calling it his greatest error. But as more observations accumulated, as more light from distant galaxies was gathered and studied, the evidence became impossible to dismiss. In the 1920s, an astronomer named Edwin Hubble made an observation that would reshape our understanding of existence itself. When he examined the light arriving from galaxies far beyond our own, he noticed something unexpected. The light was stretched, pulled toward the red end of the spectrum, as if it had been tugged by some invisible force during its long journey. And the more distant the galaxy, the more pronounced this stretching became. It wasn't just that a few galaxies were drifting away. All of them were. And those farther from us appeared to be receding faster, as if caught in a great slow tide. This pattern could mean only one thing. The universe was expanding, not through galaxies flying outward into empty void, but through space itself growing, gently carrying the galaxies along like petals floating on a rising river. It was a revolutionary idea, but the observations supported it clearly. And if the universe is expanding now, in this present moment, then logic suggests that in the past it must have been smaller, more compact, hotter, wound tighter like a spring compressed into an earlier state. The further backward you imagine, the more extreme the conditions become. Eventually, this line of reasoning led scientists to a remarkable realization. If everything is spreading apart today, and if that pattern holds as you trace time backward, then the universe must have once existed in an incredibly hot, incredibly dense state, a state where all matter, all energy, all space, and perhaps even time itself were pressed together, not into a single geometric point exactly, but into a condition so extreme that the physics we know begins to dissolve at its edges. This became the foundation for what we now call the theory of the Big Bang. A somewhat misleading name, really, since there was no bang in the way we usually imagine. There was no explosion happening within space, because space itself was what was beginning. There was no sound echoing through emptiness, no flash of light in the usual sense, just an unfolding of everything, everywhere, all at once. A moment when the universe didn't expand into something, but created the very notion of space as it expanded. It's worth pausing here, letting this settle gently in your mind, because this is where science reaches its present horizon. The Big Bang Theory doesn't actually explain the very first instant. It describes everything that happened after the universe began its expansion. It gives us a map to understand how the cosmos evolved from that early furnace of energy into the cool, structured universe we observe today, filled with galaxies and stars and the quiet darkness between them. But the actual moment of beginning, the precise nature of time, space, and cause before that expansion remains wrapped in mystery, like a distant shore hidden in fog. We don't yet know what, if anything, existed before. We may never know. Some questions rest beyond our current tools, waiting patiently for new ways of seeing. Let's look more carefully now at what we can actually describe about the Big Bang, not as an abstract concept floating in imagination, but as a sequence of physical events unfolding in time. We don't begin with a singularity in the classic sense, at least not the way it's often portrayed in simplified stories. A true singularity would imply a point of infinite density, infinite heat, infinite warping of space-time itself. And while Einstein's general relativity points in that direction when you follow the math backward, quantum mechanics resists infinities. They make the equations break down, whisper that something else must be happening at those smallest scales. What we're really encountering is a frontier, a boundary beyond which our current understanding fades into uncertainty. Not because there's nothing there, but because our mathematical language no longer speaks clearly in that realm. What we do know is this: the earliest moment we can meaningfully describe is called the Planck epoch. This is the first whisper of time after the universe began expanding, just a fleeting instant, far briefer than any interval we experience in daily life, tinier than the blink of an eye, smaller than a heartbeat, almost beyond imagination itself. If you were to stretch the entire history of the universe across the length of a football field, this moment would be thinner than a single thread of silk. It's a scale where gravity, quantum behavior, and the shape of space-time itself are all tangled together in ways we don't yet fully understand, woven into a tapestry we can't quite see clearly. During the Planck epoch, the universe was unimaginably small and incredibly hot, though even these words feel inadequate. All four of the fundamental forces we recognize today, gravity, electromagnetism, the strong nuclear force that holds atoms together, and the weak nuclear force that governs certain kinds of decay, are thought to have been unified into a single force, not just acting in harmony, but actually indistinguishable from one another, merged into one cosmic influence embedded in a shimmering quantum fabric of rapidly shifting energy and curved space-time. But we don't yet have a complete theory that can describe this state with confidence. That remains one of the greatest aspirations of modern physics, to forge a theory of quantum gravity, something that can weave together Einstein's vision of curved space-time with the probabilistic dance of quantum mechanics into a unified description of nature at its most fundamental. Until that day arrives, the Planck time remains a horizon line. We can approach it, circle around it, but we cannot see past it clearly. Yet we can describe what likely happened next as the universe continued its expansion. As it grew, and just as importantly, as it cooled, the forces began to separate from one another. This process is called symmetry breaking, and it unfolded like phases of water turning to ice, smooth and inevitable. First, gravity split away from the other forces, becoming distinct. Then the strong force separated, taking on its own character. And as temperatures continued their long descent, the electromagnetic and weak nuclear forces parted ways as well, each finding its own identity. These weren't chaotic ruptures, but graceful transitions, like different facets of a crystal revealing themselves as conditions changed. With each step, the universe became more structured, more differentiated, and new possibilities emerged from the cooling fire. One of the most dramatic transformations came just after these four separations, a moment called cosmic inflation. According to this theory, the universe didn't just expand steadily. It ballooned outward in an almost unimaginably brief instant. Space itself stretched faster than light could travel through it, not in violation of Einstein's principles, since this wasn't matter racing through space, but space itself growing, like a photograph being enlarged beyond recognition. The scale of this growth staggers the imagination. In less time than it would take a photon to cross the width of a single atom, the entire observable universe may have grown from something smaller than a grain of sand to something vast enough to contain billions of future galaxies. Why did this happen? The honest answer is we're not entirely certain, but one leading explanation involves a high energy field that briefly dominated the universe's energy budget. This field, sometimes called the inflaton, triggered exponential expansion, then decayed, releasing its stored energy into the cosmos and filling it with a uniform sea of particles and radiation. That event is sometimes called the reheating of the universe, and it marks the beginning of what we usually think of as the hot Big Bang proper, the moment when particles, atoms, and light began their long journey toward forming clouds, stars, and worlds. After inflation ended, the universe was filled with an incredibly hot, dense plasma, a seething ocean of particles, energy, and radiation swirling together. Protons and neutrons began to emerge from the raw energy, coalescing like droplets forming in mist. Then they combined into simple atomic nuclei, the first building blocks of matter taking shape. This process, called primordial nucleosynthesis, happened just a few minutes after the beginning, and it determined the fundamental composition of matter throughout the cosmos. Mostly hydrogen, the simplest element, some helium, and traces of other light elements scattered like seeds. It's astonishing to realize how much was decided in those early minutes, carved into the fabric of reality while the universe was still younger than a newborn's first breath. The balance between matter and its mirror opposite, antimatter, the overall density of the universe, the tiny seeds of structure that would one day blossom into galaxies and clusters. Much of it was established during this brief, chaotic period, governed by laws we're still working to fully comprehend. But one thing became clear even then. By this point, the universe was no longer just a quantum whisper, a mathematical possibility hovering at the edge of existence. It was a real place, filled with energy and motion and potential, alive in its own strange way. And yet, paradoxically, it was still opaque, like looking into dense fog. Light couldn't travel freely because it kept colliding with charged particles in the thick plasma, bouncing endlessly like a ball in a crowded room. The universe glowed with energy, but not with the kind of light that could travel across distances and tell a story. It would take hundreds of thousands of years, a vast stretch of patient waiting, before the cosmos cooled enough for electrons to settle into stable orbits around nuclei, forming neutral atoms, and finally allowing light to stream freely through space. When that moment arrived, when the fog lifted, the first photons of visible light began their journey across the universe, carrying with them a message from the earliest age. That ancient light is still traveling today, stretched by eons of expansion into longer wavelengths, transformed but not lost. We call it the cosmic microwave background, and it remains the oldest light we can observe, a faint whisper of creation still echoing through the darkness. Let your mind rest here for a moment, floating gently in this thought. The light that surrounded the early universe, released when atoms first formed, is still with us. It fills the sky in every direction, invisible to our eyes but present nonetheless, like a memory woven into the fabric of space itself. And it carries secrets, tiny variations in temperature, faint ripples that tell the story of how structure began to form, how the smooth early universe started to gather into clumps and clouds that would eventually become galaxies. We'll explore that ancient glow more deeply soon, but for now, let yourself drift, carried by the slow current of cosmic time, knowing that the universe's story is still unfolding, still being written in light and motion. Rest easy. The journey continues gently, just like the expansion itself, always moving, always growing, always carrying us forward through the vast and patient dark. Let's pause now and turn our attention to the faintest glow in the sky, a shimmer that isn't tied to any star or galaxy, but to something far more ancient, something woven into the very texture of space itself. Roughly 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to join together into neutral hydrogen atoms. This moment is called recombination, and it marked a profound shift in how the cosmos behaved, like a curtain slowly lifting after a long night. For the first time since the beginning, light could travel freely, no longer trapped in an endless dance with charged particles. Photons began to stream across space in every direction, carrying their stories outward into the growing universe. That light is still traveling today, still whispering its ancient song. We call it the cosmic microwave background, often shortened to CMB. It fills the universe not in patches or beams, but as a smooth, nearly uniform bath of radiation, like the soft afterglow of a fire that burned long ago. It's not visible to our eyes because time and the stretching of space have pulled its wavelengths down into the microwave part of the spectrum, far beyond what we can see. But it's there, surrounding us always, a faint embrace of ancient warmth. The discovery of the CMB was, in many ways, an unexpected gift. In the mid-1960s, two radio engineers, Arno Penzias and Robert Wilson, were working with a sensitive antenna in New Jersey. They weren't searching for relics of the early universe or trying to confirm grand theories. They were simply troubleshooting a persistent noise in their equipment, a steady hiss that refused to disappear no matter where they aimed the device or how carefully they adjusted it. They even cleaned out nesting pigeons from the antenna, thinking perhaps the birds were somehow to blame. But the signal remained, soft and constant and mysterious. What they had stumbled upon, quite by accident, was the cosmic microwave background, the cooled remnant of the universe's first light. Around the same time, a group of physicists at Princeton had been working on calculations predicting that such a glow should exist, lingering from the hot early universe. When the two teams connected and compared their findings, it became clear that this was a moment of extraordinary significance. The Big Bang was no longer just an elegant theory written in equations. It had left behind evidence, a tangible signature, a direct imprint of the early universe still visible across the entire sky. At first glance, the CMB appears astonishingly uniform. No matter where you look, up or down, east or west, its temperature is nearly the same, just a few degrees above the coldest possible temperature. But when instruments became precise enough to look more carefully, scientists noticed something truly remarkable. The smooth glow wasn't perfectly smooth after all. It had tiny ripples in temperature, fluctuations measuring just millionths of a degree, barely detectable even with our most sensitive tools, but incredibly meaningful. These fluctuations are called anisotropies, and they represent tiny differences in the density of the early universe, subtle variations in how tightly matter was packed in different regions. In some places, matter gathered just a little more closely. In others, it spread a little more thinly. These differences were small, almost negligible, but over billions of years, gravity would amplify them. The denser regions pulled in more matter, growing heavier and more concentrated, while the less dense regions remained sparse. Eventually, those tiny seeds would grow into galaxies, clusters of galaxies, vast webs of structure stretching across the cosmos. Without those ripples, there would be no structure at all, just a featureless sea of light and gas drifting endlessly without form. No galaxies, no stars, no planets, no chemistry, no life. The CMB is, in that sense, a kind of cosmic photograph, a snapshot of the universe when it was still in its infancy, long before the first star had ignited, long before Earth or our Sun existed, even as an idea. By studying the shape and scale of those ripples, cosmologists can work backward, reverse engineering the ingredients and history of the cosmos. They can measure how much of the universe is made of ordinary matter, the kind that forms stars and planets and people. They can estimate how much is dark matter, invisible material that exerts gravitational pull but doesn't emit light. And they can even detect the influence of something stranger still, dark energy, a mysterious force that affects how space expands over time. One of the most important missions to map the CMB in exquisite detail was the Planck satellite, launched by the European Space Agency. Over several years, it produced the most precise image we've ever had of the early universe, a glowing oval map of subtle color shifts, each tiny variation marking a difference in temperature and density across the sky. From that data, scientists have learned that the universe has been expanding for nearly 14 billion years. They've measured how fast it's expanding today, and they've confirmed that only about 5% of the universe is made of ordinary matter. The rest appears to be invisible, hidden from direct view. Dark matter, which pulls on galaxies through gravity but emits no light, and dark energy, which pushes the universe apart, accelerating its expansion in ways we're still trying to understand. And yet, even with all that insight, all those measurements and maps, the CMB also marks a limit, a boundary to what we can directly observe. Not because there's nothing beyond it, but because it represents the farthest light that has ever reached us. Anything that happened earlier than recombination is still hidden behind a veil of glowing plasma, like trying to see through a wall of fog. To peer further back into the past, we would need something other than light, something even older, perhaps gravitational waves from the earliest moments, ripples in space-time itself. And that leads us toward the next great mystery, not what we can see, but what we can only infer through logic and mathematics. Let's return now to those earliest moments after the Big Bang, not to the expansion itself, but to what it left behind. Energy, heat, motion, and eventually, matter. One of the most profound puzzles in cosmology is deceptively simple to state. Why is there something rather than nothing? The laws of physics, as we currently understand them, suggest that matter and antimatter should have been created in equal amounts during the universe's first moments. For every proton, an antiproton. For every electron, a positron. And when these opposite particles meet, they annihilate each other, returning to pure energy in a flash of light. In theory, the early universe should have been perfectly symmetrical, balanced like two sides of a scale. And yet, it wasn't. When we look around today, we see a universe made almost entirely of matter. Antimatter is rare, fleeting, mostly produced in particle accelerators or high-energy cosmic events. Somewhere, somehow, in those first fractions of a second, matter gained the upper hand, not by much, perhaps just one extra particle of matter for every billion pairs that annihilated, but enough. When all the annihilations were finished, that tiny excess remained, and from that small remainder came everything. Every atom in every star, every molecule in every living cell, every grain of sand on every shore. This imbalance, this slight triumph of matter over antimatter, is called baryon asymmetry, and to this day, it remains one of the most intriguing open questions in physics, a puzzle that sits at the heart of why we exist at all. What tipped the scales even slightly? Why did matter come out just a little bit ahead? Physicists have proposed several mechanisms that might explain it. Delicate processes hidden in the fabric of the universe's earliest moments. One possibility is that the laws of physics themselves aren't perfectly symmetrical, that there are subtle differences in how the universe treats matter and antimatter. These are called CP violations, a term that refers to how certain particles behave under transformations of charge and parity. Scientists have observed these violations in laboratory experiments, in the decay of certain particles, but not yet in a way that fully explains the imbalance we see written across the cosmos. Another idea involves particles that no longer exist, heavy exotic forms of matter that may have emerged briefly during the earliest moments of the universe and then decayed in asymmetric ways. These decays could have favored matter over antimatter in just the right proportions, setting the stage for everything that followed. But these particles, if they ever existed, vanished almost instantly, leaving only their influence behind, like footprints in sand that have been mostly washed away by time. Whatever the mechanism, whatever small asymmetry tipped the balance, the result was profound and irreversible. That slight excess of matter, perhaps just one part in a billion, would go on to form every atom, every molecule, every structure we can observe. Without it, the universe would have been empty, filled only with photons and empty space. No galaxies spiraling slowly through the dark, no stars forging elements in their hearts, no chemistry, no complexity, no awareness. The entire visible universe, everything we can touch or see or imagine, is built on what might be described as a cosmic rounding error, a delicate imbalance inscribed into the laws of nature at the moment of creation. And what's even more humbling is this: we don't know why it happened. Not fully, not yet. We can describe the imbalance. We can measure it in the matter around us. But the underlying cause, the deeper reason, remains just out of reach, like a word on the tip of the tongue. It's as if the universe left us a clue written in light and matter, but not the key to decode it completely. And so scientists continue to search in particle accelerators where matter and antimatter collide, in experiments studying rare particle decays, in the faint echoes of ancient radiation, for any sign of how the laws of physics might favor matter just enough to create a universe capable of asking questions. This search isn't merely academic or abstract. It touches the deepest questions we can ask as conscious beings. Why is there something rather than nothing? Why do the laws of nature permit a world like ours to emerge from such a fragile beginning? These are not easy questions, and they may not have simple answers. But science, moving gently, step by careful step, can sometimes circle closer to the heart of mysteries, can illuminate the edges even when the center remains dark. In the end, what we call the universe, the stars scattered across the night sky, the galaxies spiraling in their slow dance, the atoms in your fingertips and the breath in your lungs, all of it comes from that leftover sliver, that tiny imbalance that the early universe somehow preserved instead of erasing. And from there, from that small excess, structure began to emerge. Gravity began to take hold. The densest regions of matter began to collapse inward, drawing in more material, compressing, heating, preparing for transformation. These regions would eventually become the first stars, not yet formed, not yet shining, but already destined, already written into the fabric of expanding space. The universe, once smooth and uniform like a calm sea, was beginning to ripple, to clump, to become uneven in ways that mattered deeply. But before stars could ignite, before galaxies could spiral into being, and long before planets could take shape in the darkness, the universe had to pass through a long, quiet phase, an era without light, without structure, almost without name, a time that cosmologists now call the cosmic dark ages. That is where our journey will carry us next. The universe had light once, that early glowing fog of photons released when atoms first took form. But that light faded over time, stretched thin by expansion, cooled by distance, diluted by the growing vastness of space. And what followed was a kind of stillness, a deep darkness, a long cosmic night that stretched on for hundreds of millions of years. This era is called the Cosmic Dark Ages, and it represents a transitional period between the bright infancy of the universe and the star-filled cosmos we see today. During this time, the universe was still full of matter, hydrogen and helium atoms drifting quietly through expanding space, slowly gathering into denser and denser clumps under the patient pull of gravity. But there were no stars yet to illuminate the void, no galaxies to paint light across the darkness. The photons from the Big Bang still existed, but they were no longer visible, stretched into longer and longer wavelengths, and no new light had yet been born to replace them. If you could have somehow stood in the middle of space during this period, suspended in the emptiness, you would have seen nothing at all. No starlight glinting in the distance, no planets reflecting borrowed glow, no movement beyond the slow, invisible collapse of vast hydrogen clouds drawing together under gravity's gentle hand. The universe was enormous and utterly dark, waiting patiently, preparing quietly for something extraordinary. Over time, across millions and millions of years, gravity continued its slow, steady work, never rushing, never pausing. The denser regions pulled in more gas from their surroundings, growing heavier and more concentrated. Tiny fluctuations in density, seeded back in the earliest instance of the universe, began to grow and deepen. These clouds of hydrogen collapsed gradually, sinking into themselves, deepening into knots of pressure and rising heat. And at a certain threshold, one we know well from studying stars in the present day, fusion began. Hydrogen atoms pressed so closely together that they merged, releasing energy in a cascade of light and warmth. The first stars flickered into being, breaking the long silence. They were likely much larger than most stars we see today, perhaps hundreds of times the mass of our own sun, burning fiercely and living briefly. These were the population 3 stars, the first generation, born from pure primordial hydrogen and helium, untouched by heavier elements because no such elements existed yet. They lived fast and died young, burning brilliantly for a cosmically brief time before collapsing into black holes or erupting in massive supernovae that scattered their inner contents across space. Their light marked the end of the cosmic dark ages, not suddenly, not all at once, but gradually, unevenly, like dawn breaking slowly over a landscape. As these early stars ignited across different regions of space, they poured ultraviolet radiation into their surroundings, stripping electrons from nearby hydrogen atoms and turning cold, neutral gas back into an ionized plasma. This process is called reionization, and it slowly peeled back the veil of darkness that had covered the cosmos, carving glowing bubbles of transparency around each young star and cluster. Rionization didn't happen overnight, or even over a single era. It unfolded gradually, spreading unevenly across the universe over hundreds of millions of years. The first stars formed in small clusters, primitive gatherings that would eventually grow into galaxies. Their radiation carved glowing bubbles around them, clearing pockets of transparency in the cosmic fog. Over time, these bubbles grew larger and began to merge, overlapping and connecting, until eventually the fog of neutral hydrogen was mostly cleared away. Space became transparent again, open to light, ready to tell its story. This phase of the universe, from the ignition of the first stars to the completion of rionization, is incredibly difficult to observe directly. The light from those early stars is faint, stretched by the expansion of space, scattered across billions of years of distance. But new tools, like the James Webb Space Telescope, are beginning to glimpse galaxies that formed just a few 100 million years after the Big Bang, offering our first direct look into that long-lost era, that time of transition when the universe awoke from its long sleep. These early galaxies were smaller, denser, and more chaotic than those we see in the present. They were messy, turbulent, filled with young massive stars burning through their fuel rapidly. But they were real, tangible, the first true cradles of complexity, powered by gravity and fusion, lit from within. And with them came the first steps toward greater complexity, the first heavy elements, the building blocks of everything that would come later. Planets, oceans, mountains, carbon, life itself. When the first stars reached the end of their brief lives, they did not vanish quietly into the night. Many of them transformed in brilliant supernovae, scattering newly forged elements across space like seeds carried on the wind. Carbon, oxygen, nitrogen, iron, silicon, and more. Elements that had never existed before, born in the hearts of dying stars and released into the cosmos. These materials seeded the next generation of stars, and those stars in turn would create even more elements. Around some of those later stars, small disks of dust and gas began to form, swirling slowly, colliding and sticking together, gradually shaping themselves into rocky worlds and gas giants, moons and asteroids, entire solar systems taking shape in the darkness. Galaxies began to assemble into larger structures, pulled together by gravity. They collided with one another, merged, and spun into elegant spirals and smooth elliptical forms. The cosmic web, a vast filamentary network of dark matter and visible galaxies, began to emerge across the universe, connecting clusters and superclusters in a delicate lacework of structure. The universe was no longer smooth and dark. It was alive with light, texture, motion, and complexity. By around 1 billion years after the Big Bang, the universe had entered a new era, one that looked, in its broad outlines, much like the cosmos we observe today, still evolving, still expanding, still changing, but now lit by countless stars and shaped by the steady hand of gravity. The long silence had ended, and the symphony had begun, a song that continues even now. Billions of years later, as new stars are born and old ones fade, as galaxies drift and merge, as the universe continues its endless dance through time. Let yourself rest here for a moment, floating gently in this thought that we are part of that story, descendants of stardust, children of the cosmic dark ages, living in the light that followed. By the time the universe had aged a few billion years, it had begun to take on a shape that would feel almost familiar, at least from a great distance. Galaxies had formed across the vastness of space, glowing with the light of billions of stars, threaded together by gravity into enormous structures. Some spun gracefully into elegant spirals, arms trailing outward like cosmic pinwheels. Others clustered into tight elliptical knots, smooth and featureless. Great voids stretched between them, empty expanses like bubbles in a foam, creating a texture that was both delicate and vast. The universe, once uniform and smooth like undisturbed water, had become richly textured, woven with complexity. And yet, through all of this, one thing never stopped: the expansion. Ever since the Big Bang, space itself had been stretching, growing, carrying galaxies along with it. And as galaxies moved apart with the flow of this expansion, the light they emitted was stretched too, pulled toward longer, redder wavelengths, like a note sliding down in pitch. This phenomenon is known as cosmic redshift, and it provides one of our clearest windows into the scale and speed of the universe's growth. The more distant a galaxy is from us, the more its light has been stretched during its journey, and the faster it appears to be receding into the distance. This idea that the universe is expanding was first confirmed nearly a century ago through the careful work of Edwin Hubble. By measuring the redshift of distant galaxies and comparing it to their distances, he discovered a clear and undeniable pattern. The farther away a galaxy was, the faster it appeared to be moving away from us. It was as if space itself was stretching in every direction at once, carrying everything along with it. For many decades after this discovery, scientists naturally assumed that the expansion must be slowing down over time. After all, gravity pulls things together, and with so much matter scattered throughout the universe, wouldn't that gravitational attraction eventually slow the expansion, perhaps even halt it entirely? Some cosmologists even imagined a scenario where the universe might one day stop expanding and collapse back into itself, a reversal called the Big Crunch. But then, in the late 1990s, something completely unexpected was discovered, something that would transform our understanding of the cosmos once again. Two independent teams of astronomers were studying distant supernovae, brilliant stellar explosions that serve as standard candles, allowing us to measure enormous cosmic distances with precision. What they found shocked the scientific community and overturned decades of assumptions. The expansion of the universe wasn't slowing down at all. It was speeding up. Somehow, some force or property of space itself was causing the universe to expand faster and faster over time, accelerating outward like a car pressing down on the gas pedal. That force has been given a quiet, enigmatic name: dark energy. Dark energy is not a substance we can see or touch or collect in a jar. It doesn't glow like stars or cluster like galaxies. It doesn't behave like matter in any familiar way. Instead, it seems to be an intrinsic property of space itself, a kind of energy woven into the vacuum, gently but relentlessly pushing everything apart. Today, dark energy is thought to make up roughly 70% of the total energy content of the universe. It's the dominant force in cosmic evolution, the invisible hand guiding the fate of everything we can observe. And yet, it remains almost entirely unexplained, one of the deepest mysteries in all of science. We don't know if dark energy will remain constant over time, or if it might change, growing stronger or weaker as the universe ages. We don't know what causes it, whether it's a true cosmological constant, an unchanging feature of space-time as Einstein once proposed, or something more dynamic, like a slowly evolving field that shifts and changes as the universe expands. What we do know is that its effects are profound and far-reaching. Over time, as dark energy continues to drive the expansion, galaxies that are not bound together by gravity will drift farther and farther apart. Eventually, distant galaxies will slip beyond the horizon of visibility, not because they're moving through space in the usual sense, but because space itself is expanding so quickly that their light will never be able to reach us. In the far future, many billions of years from now, the universe may become a much colder, lonelier place. The stars will still shine for a time, burning through their fuel, but beyond a certain point, only the closest galaxies will remain visible to any observer. The cosmos, once bright and buzzing with activity and light, will fade gradually into quiet isolation, each galaxy island becoming its own separate universe, cut off from all the others. And yet, even in that distant future of silence and separation, the universe will continue to evolve, to change, to move forward through time. Stars will age and die, their fuel exhausted. Some will collapse into white dwarfs, cooling embers no longer capable of fusion. Others will collapse further into neutron stars, incredibly dense remnants held up by quantum pressure. Still others will cross the final threshold and become black holes, regions of space-time so warped that not even light can escape their grasp. But new stars will also be born, at least for a time, formed from the scattered ashes of earlier generations, clouds of gas and dust collapsing under gravity's patient pull. Over vast timescales, though, trillions upon trillions of years into the future, star formation will slow and eventually cease. The fuel will run low, the reservoirs of hydrogen and helium gradually depleted. Fewer and fewer stars will be born, and the galaxies will grow dim, their light fading like candles burning down. One by one, the lights will go out, and the universe will pass into what some cosmologists call the degenerate era, a time dominated not by shining stars, but by their remnants, white dwarfs drifting quietly through the void, neutron stars spinning slowly in the darkness, black holes swallowing whatever matter drifts too close, growing slowly, patiently, over unimaginable spans of time. Eventually, over timescales so long they beg a description, even the black holes may vanish, evaporating slowly through a process called Hawking radiation. According to quantum mechanics, black holes aren't entirely black. They emit faint radiation from their event horizons, losing mass bit by bit, atom by atom, over eons. A black hole with the mass of the Sun would take longer than the current age of the universe many times over to evaporate completely. But larger black holes, those with millions or billions of solar masses, would take even longer, time spans so vast that the numbers lose all meaning. And if dark energy continues to accelerate the expansion as it does today, the universe may thin and cool until it approaches a state of absolute stillness. No stars, no warmth, no motion, just particles and space stretching endlessly into an eternal twilight. But that too is only one possibility among several. The future is vast, uncertain, and full of quiet questions we cannot yet answer. The universe is not static, and it never has been. From the very first moment of the Big Bang, It has grown and changed, evolved and transformed. Particles emerged from energy, light escaped from plasma, galaxies spun slowly into being across the darkness. Stars lived and died, forging elements and seeding space with the raw materials for planets and life. And even now, billions of years later, everything is still in motion, still unfolding, still writing its story across the canvas of space-time. But what lies ahead, in the deep future, beyond the reach of stars? If dark energy remains constant, if the force accelerating the expansion of space continues unchanged, then the universe will grow colder and darker over time, fading gradually into what cosmologists sometimes call the Big Freeze, a future where expansion never stops, where galaxies drift beyond each other's horizons, where eventually the stars burn out, the black holes evaporate, and all that remains is a thin, silent fog of particles drifting through an ever-expanding void. It's not a dramatic ending, no sudden collapse or explosion, just a long, slow exhale into stillness, like a breath that never quite finishes. But the Big Freeze isn't the only possibility, the only path the universe might take. Some physicists have imagined a different fate, one where dark energy doesn't remain constant, but grows stronger over time, accelerating faster and faster. In this scenario, the acceleration of the universe would increase relentlessly, slowly tearing apart larger and larger structures. First, galaxy clusters would unbind, their members drifting apart. Then galaxies themselves would be pulled apart, their stars scattered into isolation. Eventually, even solar systems would unbind, planets torn from their orbits. And in the final moments, space itself could become so unstable, stretching so violently, that even atoms might be ripped apart, their electrons torn from their nuclei, their very structure undone. This idea is called the Big Rip. And while it's more speculative, it follows logically from certain models of dark energy. It wouldn't happen suddenly or without warning. The process would unfold over billions of years, accelerating gradually. But in the end, nothing would remain bound together. Even the fundamental building blocks of matter might dissolve into the churning fabric of space-time. Then again, perhaps the expansion won't continue forever at all. Some cosmological models suggest that dark energy might not be constant or growing, but could instead reverse its influence. The universe, after reaching a certain point in its expansion, might slow down and begin to collapse inward, falling back on itself. Heat would rise again, density would increase, galaxies would collide and merge, and eventually everything would be drawn back together in a reversal of the Big Bang, an event known as the Big Crunch. In this scenario, the universe would end much as it began, compressed into an incredibly hot, incredibly dense state, all structure erased, all complexity undone. But some theories go further, suggesting that the Big Crunch might not be an ending at all, but a transition, a moment of transformation that sparks a new expansion, a new Big Bang. From this idea emerges the concept of a cyclic universe, a cosmos that breathes in epochs, forever expanding and contracting, dying and being reborn, with no true beginning and no final end. The idea of a cyclic universe is ancient, whispered in myths and philosophies long before science gave it mathematical form. A cosmos with no absolute origin or ultimate conclusion, only transitions, deaths that lead seamlessly into new births, collapses that ignite fresh expansions. A universe that breathes like a living thing, inhaling and exhaling across unimaginable stretches of time. Modern physics doesn't rule this out entirely. Some theories, like loop quantum cosmology, suggest that the Big Bang may not have been the absolute beginning of everything, but rather a rebound, the result of a previous universe collapsing under its own gravity and then bouncing back into expansion. Other ideas imagine even more complex structures, multiverses, where our universe is just one bubble among countless others, each with its own laws and histories, or quantum fluctuations constantly spawning new regions of space beyond our cosmic horizon, forever out of reach. We don't yet know if these ideas are testable, if they can ever be confirmed or ruled out through observation and experiment. They remain, for now, at the edge of speculation, beautiful mathematical possibilities that emerge from extending our theories beyond what we can directly see. But they offer something deeply human, a sense that the story may not be over, that the cosmos may contain more chapters than we can yet imagine, more depth and richness than our current tools can reveal. And yet, even if the distant future remains unknowable, wrapped in uncertainty and possibility, the present is not. We are here now, in this brief and luminous moment between the darkness that came before and the silence that may come after. The future of the universe stretches far beyond our lifetimes, beyond the lifespan of stars, beyond the slow dance of galaxies. It's a canvas of unimaginable time, painted not with brushstrokes, but with motion, temperature, gravity, and the ever-expanding fabric of space itself. And while we may never witness the universe's distant fate with our own eyes, we are undeniably part of its present, a momentary ripple in an ocean of change. We live on a small rocky planet warmed by a medium-sized star, orbiting peacefully within a spiral galaxy, drifting through a universe that began in unimaginable heat and may end in profound silence. The same physical laws that govern the brief lives of subatomic particles also shape the destinies of stars and galaxies. The same forces that bent space-time in the earliest moments of creation now guide the future, writing it slowly across billions of years. To study the cosmos, to trace its history from the Big Bang to the present and beyond, is not just to look outward into the night sky. It's to see ourselves differently, to recognize that we are part of something vast, ancient, and ongoing. We are not separate from the universe's story, standing outside it as detached observers. We are woven into it, made from its matter, shaped by its forces, alive because of its particular balance of laws and constants. We are a brief line in the universe's unfolding poem, a moment of awareness in a cosmos that stretches across time and space beyond comprehension. And so, we have followed the thread gently from the first spark of time, through the long silence and the birth of stars, outward to the cosmic web of galaxies, and forward to the far horizon of what may yet come. We've spoken of particles smaller than imagination, and distances that light takes eons to cross. We've wandered through darkness, not as something to fear, but as the quiet space from which all things emerge, the canvas on which light paints its story. Rest easy now. Let your thoughts drift like distant galaxies, carried by the slow current of expansion. The universe continues its journey, and so do you, moving through time, part of the whole, never separate, always connected. If you're still awake now, perhaps you're resting quietly, your breathing slow and steady, your mind softened by this long journey through time and space. Or perhaps you've already drifted off, floating somewhere between waking thought and dream, carried gently by waves of starlight and the quiet rhythm of cosmic expansion. Wherever you are in this moment, however far you've traveled along this path, know that you are exactly where you need to be. There is no destination to reach, no finish line to cross, only this gentle drifting, this peaceful letting go. Let's bring our attention now to something both vast and intimate, both distant and deeply personal. The question of meaning in a universe so large, so old, so seemingly indifferent to our small lives. When we contemplate the scale of cosmic time, when we think about billions of years stretching behind us and trillions stretching ahead, it's natural to feel small, even insignificant. What does it mean to be human, to be conscious, to care and dream and wonder in a universe that was here long before us and will continue long after we're gone? But perhaps there's another way to see it, a gentler perspective that doesn't diminish us, but places us within the story in a different light. We are not separate from the universe, not strangers visiting from some other realm. We are made of the universe, literally constructed from atoms forged in the hearts of ancient stars, built from the same matter that swirled in the early cosmos, shaped by the same forces that bend space-time and guide galaxies through the dark. Every atom in your body, every molecule, every cell, was once part of a star that lived and died billions of years ago. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was created through nuclear fusion in stellar cores and scattered across space. When those stars reach the end of their lives, you are, in the most literal sense, made of stardust, a collection of ancient elements temporarily arranged into the particular pattern that is you. And not just you, but every living thing, every tree and bird and blade of grass, every ocean and mountain and grain of sand. All of it connected, all of it part of the same unfolding story. The universe, through a long chain of events stretching back to the Big Bang, has become capable of looking at itself, of wondering about its own origins and fate. Consciousness, awareness, the ability to ask questions and seek answers, these are not foreign to the cosmos. They are expressions of it, ways the universe explores its own nature. When you look up at the night sky and feel wonder, that is the universe wondering about itself. When you ask where everything came from, that is the universe asking about its own beginning. You are not outside the story looking in. You are the story becoming aware of itself. And that awareness, brief as it may be on cosmic timescales, is precious beyond measure. It's easy to focus on the enormity of space and time, on the vast distances between stars, on the eons that separate the Big Bang from the present. But scale is only one way to measure significance. A moment of joy, a connection with another person, the quiet beauty of a sunrise. These things are not diminished by the size of the universe. If anything, they become more remarkable, more meaningful, because they exist at all. Because in a cosmos governed by physical laws, shaped by randomness and necessity, there arose beings capable of experiencing beauty, capable of love, capable of wondering about their place in the grand scheme. The universe did not have to be this way. The constants of nature, the strengths of the fundamental forces, the properties of matter and energy, all of these could have been different. And if they had been, even slightly, the cosmos might have evolved in entirely different ways. Stars might never have formed. Heavy elements might never have been created. Planets might never have coalesced from clouds of dust. Life, consciousness, the particular arrangement of atoms that makes up a thinking, feeling being, might never have emerged. And yet, here we are. The universe unfolded in such a way that it became capable of reflecting on itself, of asking questions, of seeking understanding. Whether that was inevitable or improbable, guided or accidental, remains an open question, one that science may never fully answer. But the fact itself is undeniable. We exist. We are aware. We are part of the cosmos, shaped by its history, connected to everything that came before. Let yourself rest in that thought for a moment. You are not separate. You are woven into the fabric of everything, connected through time and matter to the first stars, to the early universe, to the moment when space itself began to expand. Your existence is a thread in a vast tapestry, brief but integral, fleeting but real. Now, as we near the end of our journey together, let's turn our attention inward, not to science or cosmology, but to the simple experience of being here, now, in this quiet moment. The universe will continue its slow evolution, whether we understand it fully or not. Galaxies will keep drifting apart, stars will keep being born and dying, space will keep expanding, carrying everything along with it. But right now, in this present instant, you have the gift of awareness, the ability to pause and reflect, to let your mind wander among the stars, and then return gently to the body, to the breath, to the quiet stillness of rest. There's something profoundly peaceful about cosmic time, about the way the universe moves so slowly, so patiently. Nothing in the cosmos is rushed. Stars take millions of years to form, billions of years to burn through their fuel. Galaxies drift and merge over timescales that make human history seem like the blink of an eye. The universe doesn't hurry. It simply unfolds moment by moment, following the laws of physics with a kind of effortless grace. Perhaps there's wisdom in that, a lesson we can carry from the cosmos into our own lives. The universe teaches patience, teaches that change happens gradually, that transformation is a slow process, that even the grandest structures, galaxies and stars and planets are built up slowly over time, piece by piece, atom by atom. It teaches humility too, reminding us that we are small in space and time, but not insignificant. Our smallness doesn't diminish us. If anything, it connects us to something larger, something enduring, something beautiful. And it teaches wonder, the kind of open-hearted curiosity that looks at the night sky and feels awe, not because we understand everything, but because we understand enough to know how much remains unknown, how many mysteries still wait to be explored. Wonder is not the enemy of knowledge. It's the beginning of it. It's what drives us to ask questions, to seek answers, to push the boundaries of what we can see and understand. And even when we reach the limits of our current tools, when we stand at the edge of what science can tell us, wonder remains, quiet and patient, inviting us to keep looking, keep asking, keep exploring. As you rest now, let your mind drift gently among the images and ideas we've explored together. The early universe, impossibly hot and dense, expanding outward in all directions. The first light streaming freely through space as atoms formed. The long cosmic night, silent and dark, waiting for the first stars to ignite. The slow assembly of galaxies, clusters, the vast cosmic web stretching across billions of light years. The patient work of gravity, pulling matter together, shaping stars and planets, creating the conditions for complexity to emerge. The mystery of dark matter, invisible but present, holding galaxies together, the enigma of dark energy, pushing the universe apart, accelerating its expansion toward an uncertain future. The delicate balance of forces and constants that allowed stars to shine, elements to form, life to arise. All of it connected, all of it part of one continuous story, a story that began nearly 14 billion years ago and continues still, unfolding in every moment, in every atom, in every breath you take. Science is often thought of as cold, mechanical, a collection of facts and equations devoid of emotion. But that's not quite right. Science is a way of asking questions about the world, about the universe, about ourselves. It's a method for seeking truth, for testing ideas, for building understanding piece by piece. And at its heart, science is driven by the same thing that brings you here tonight, listening to stories about stars and time and the beginning of everything. Curiosity, wonder, a desire to understand, to see more clearly, to connect with something larger than ourselves. The equations and observations, the telescopes and satellites, the careful measurements and theoretical models, all of these are tools in service of something fundamentally human. The need to know, the longing to understand where we came from, where we're going, what it all means. And while science can answer many questions, provide frameworks for understanding the physical universe, it cannot answer every question. There are mysteries that may always remain beyond our reach, questions that sit at the boundary between physics and philosophy, between knowledge and wonder. What came before the Big Bang? Why does the universe exist at all? Is there meaning woven into the fabric of reality? Or do we create meaning through our choices, our connections, our brief moments of awareness? These are not questions with simple answers, and perhaps they're not meant to be answered simply. Perhaps the value lies not in finding final answers, but in the asking itself, in the way questions open our minds, expand our perspectives, invite us to see the world and ourselves in new ways. The universe, in all its vastness and mystery, invites us to wonder, to question, to explore, and in return, it offers something precious, a sense of connection, a feeling of being part of something ancient and ongoing, a reminder that we are not alone, not separate, but woven into the fabric of everything. So as you rest now, as your breathing deepens and your thoughts begin to dissolve like mist in morning light, carry this with you. You are a child of the cosmos, made of stardust, shaped by billions of years of cosmic evolution. You are a way the universe has become conscious of itself, a brief but beautiful moment of awareness in an ocean of time. And though your life is short compared to the lifespan of stars, though your body is small compared to the scale of galaxies, you matter. Your existence is not an accident or a mistake. It's a part of the story, a thread in the tapestry, a note in the cosmic symphony that has been playing since the beginning of time. The universe continues its journey, expanding outward, cooling slowly, writing its future across the canvas of space-time. Stars will keep shining until their fuel runs out. Galaxies will keep drifting through the dark. Space will keep stretching, carrying everything along with it. And somewhere, on a small rocky planet, orbiting an ordinary star in an unremarkable galaxy, beings like you will keep looking up at the night sky, keep asking questions, keep seeking understanding, keep marveling at the beauty and mystery of it all. If this journey has brought you comfort, if it has eased your mind or helped you drift towards sleep, if it has sparked even a small flame of wonder or curiosity, then it has served its purpose. Consider gently tapping the like button if you feel moved to do so. It helps these quiet journeys reach others who might need them, other souls seeking rest and wonder in equal measure. And consider subscribing to the Sleepy Science channel so that more stories like this one can find their way to you, offering comfort and curiosity whenever you need them. And now, as you rest beneath the quiet stars, as galaxies turn slowly in the darkness beyond our sight, as ancient photons whisper across unimaginable distances, carrying messages from the early universe, just remember this: the universe is still unfolding, still drifting through time, still singing softly in the language of physics and light. And you are part of that song, a note in the melody, a ripple in the ocean of existence. Rest easy now. Let go of the day's worries, the weight of thoughts, the pull of tomorrow. Just drift gently, peacefully, carried by the slow current of cosmic time. The stars will keep shining, the universe will keep expanding, and you, for this brief and precious moment, can simply rest, held softly in the vast embrace of everything that is, everything that was, and everything yet to come. Sleep well, traveler. The cosmos watches over you, patient and endless, ancient and new. And under the deep, dark silence of space, beneath the gentle glow of distant stars, the story continues, always continues, forever unfolding in the quiet dance of time and light. Good night.